Welcome, everybody. Thanks for coming to a new podcast. We're doing a little mini-series on amplifiers, and this time we're going to talk about VSWR. And my guest today is Nick Jones. Nick, thanks for coming.
Hello, thanks for having me.
Nick's the product manager from the factory where the amplifiers are made. He does the marketing, works closely with the engineering and the and those kind of things. So Nick has a long history of amplifier production, manufacturing, engineering. So we're really lucky to have him. Thanks for coming, Nick. So let's start with so the topic of this conversation is VSWR, and VSWR is basically like a ratio of reflections. Can you explain that a little bit better?
Yeah. So VSWR stands for voltage standing wave ratios. So it's a ratio of minimum to maximum voltage on a transmission line. So, and it's the match between the amplifier and the load. So in an ideal situation, amplifiers work in a 50 ohm on a 50 ohm line, and the ideal match between a load and an amplifier is a ratio of 1:1. But that's theoretical, so it never happens. So the amplifiers always have to work into a VSWR condition, whether it be a light VSWR condition or a heavy VSWR condition. And what we mean by that is the amount of power that's reflected back into the amplifier due to the quality of the match between the amplifier and the load.
And so, I mean, it could be like, it could be obviously the no antenna is exactly 50 ohm across the entire frequency range, right?
Yeah.
And it also could be you make a mistake in your setup and you forget to set up your cable or something like that. So in the end, you're shooting the RF energy into an open circuit or something like, or God forbid, a short. I mean, what happens in a short? Do the amplifiers blow up?
Potentially, yeah. So 100% of the energy from the amplifier is reflected back into the amplifier. And some amplifiers, well, in that condition, all amplifiers on the market should be able to protect themselves in that condition. And there's different ways that this can be done. So some amplifiers, the design topology within them use many small transistors. And that type of design topology can be used to hardware protect the amplifier. Now, what I mean by that is each transistor within that amplifier can take its own reflected power back into itself. So the amplifier could be switched on, no antenna, no load connected at all, and would sit there quite happily. Whereas if we go for a design of amplifier where we use high power transistors, then we're talking about voltage breakdown and temperature dissipation of the transistor. So it's easier to combine less transistors. We always have to combine transistors to make high power amplifiers. But in those conditions, those types of high power transistors may not necessarily be able to take all of the power reflected back into them. So in those instances, the amplifier itself has to protect the transistors within it from such conditions. And to do that, they use what's called fallback. So the amplifier has a coupler on the output that measures the forward and reflected power. And when the reflected power gets up to a certain level detected by the amplifier itself, the amplifier will internally turn down its own gain. So there'll be a voltage variable attenuator on the input.
Okay. Is this related to amplifier performance directly, or is this really a protection mechanism?
It's both. So depending on your application, if we're talking about radiated immunity, typically for standard systems, you won't have very heavy VSWR conditions between 80 megs and a gig. If we go down in frequency, if we go down to 10 kilohertz to 230 megahertz, and we're talking ISO 11451 for full auto, we're talking 10 kilowatts potentially of amplifier power. And the VSWR of those antennas, when you get down to 30 megahertz, is really quite significant. So the amplifier design has to be able to push through the VSWR condition of the antenna to generate the field strength.
Okay, and I mean, so my amplifier experience is honestly maybe 20 or 30 years old, but I remember. So if you didn't have your amplifier your measurement device, in my case, kind of matched, there was a chance of them being damaged. I mean, it sounds like that's not the case anymore, right?
It can be. It depends. If you take a product that can be hardware protected, then it's far less likely to be damaged due to VSWR conditions. If we take products that use fallback to protect themselves due to the design topology, then if the VSWR conditions change at a gradual rate, then the internal circuitry can react to that change and react quick enough to protect the amplifier if it exceeds its VSWR limit. But it's not unheard of that if a connection to an amplifier has been mismade, as you've previously just said, or an amplifier is left in a condition where it's open circuit, we have to heavily rely on the speed of our protection circuitry within the amplifier to protect it. And if that doesn't kick in quick enough, which it always should, but if in a given instance it doesn't, then that RF energy will get back into the transistors, and that's when the transistors can be damaged.
Mm-hmm. And so what is fallback in a nutshell?
So fallback is, as I tried to explain earlier, but maybe not so well, the power is reflected back into the amplifier. So the amplifier will have a protection circuit internally. So when it gets to a given ratio, 4:1, which is 40%, 6:1, which is 50%, the amplifier will it detects that on the coupler that's internal to the amplifier or an external coupler, and it detects that amount of power, and it starts to basically limit the amount of output power the amplifier can give. And it does this by, if the signal generator on the input is still trying to increase to achieve the field strength, there's a voltage variable attenuator on the input of the amplifier that starts to attenuate that input signal. So basically, you have a situation where the input is going up, but the amplifier internally will not transmit that input power to the amplifier, maintaining it at its current output level.
Okay. Is that how we do it in all cases, or are there different topologies that we use to different
topologies? So if you take an amplifier that operates from 80 megahertz to 1 gig, we have to use, you can use different transistor technologies from LDMOS to GaN. And typically most manufacturers use GaN for all of their products now, because it's easier to use for the design purposes. But the transistors that we use are high power transistors, because it's about the match. It's finding the sweet spot of the amplifiers, what the application expects of the amplifier, the heat the amplifier generates, the size of the amplifier. So for most amplifiers, 80 megahertz to a gig, we use fallback to protect the amplifiers because of the topology of the amplifier and the large transistors that we use in those designs. If you then go above a gigahertz, for instance, for our 4G amplifiers or our 6G amplifiers, we use lots of small transistors within those products. So we don't use fallback to protect them from heavy VSWR conditions because we don't need to.
Okay, and do we do something special? I mean, what's our advantage? I've heard you talking about our advantage and our topology. What's different?
So with our 4G and 6G products, because of the topology of the smaller transistors that we use and how we combine them together, they are very, very reliable products within VSWR conditions. So with radiated immunity conditions over those frequencies, we don't typically see heavy VSWR situations, but there are applications outside of radiated immunity where there may be heavier VSWR conditions, and makes the amplifiers suitable for many applications. If the VSWR condition is heavy, then the amplifier can drive through that condition. It will transmit full forward power when it sees a heavy VSWR or heavy amount of reflective power coming back. So it doesn't shut down, it just keeps trying to drive 100% of its power into the load that it sees.
Okay. That's an advantage, especially in other applications outside EMC. Yeah. Any last words before we end this, I want to thank you very much for coming. If you have anything you'd like to say that we missed, please feel free now.
I don't believe we've missed anything. But if I think I'll give you a call.
Okay. Thanks a lot, everybody, for listening. Speaking of other applications, stay tuned for the next podcast where we're going to talk about amplifiers and other applications, plus EMC. Obviously, we're known as an EMC company, but we're going to talk. Nick has a lot of experience with amplifiers and other applications, and that's one of the topics of the next podcast. So, Nick, thanks for coming. Everybody, thanks for tuning in, and we'll see you next time.
Thank you.